Hello, folks, and welcome to the second part of Lecture 20. So, we're going to spend this half of this lecture talking about how to interpret confidence intervals. So, we've seen a little bit on finding them, and now we are going to be thinking about how to actually make sense of them once we find them. So, let's suppose that we are trying to find the average mass of bolts manufactured by a given company. So we have a population, and each random variable in this population represents the mass of one of the bolts that this company could conceivably produce and ship to us. So the mass of the first bolt that they would ever ship to us is x sub 1, the mass of the second is x sub 2, and so forth. We will also, as we mentioned last time, assume that we actually know the population variance. This is not a realistic assumption, but let's make it for the sake of simplicity for now. So suppose that we know the variance inherent in these bolt masses is 4. Maybe grams is the unit we're using here. I'm not too worried about units. So our plan is to buy 100 of these bolts and mass all of them and find a 95% confidence interval for the population mean, for the average mass of all of the bolts this company could ever produce. So based on the work that we did in part 1 of this lecture, our 95% confidence interval is going to take this form. We're going to have the sample mean for our sample of size 100. We'll be subtracting off the 1.96 that corresponds to a 95% confidence interval. And we're multiplying that by our standard deviation, which is 2. We had a variance of 4, so sigma is 2 here. And dividing that by the square root of the sample size. Our sample size is 100, and the square root of 100 is 10. Now, we now can conceive of this interval as a random interval. It depends on which bolts these folks ship to us and what their masses happen to be as to what our sample mean is going to be. So at this point, this interval is a random quantity. It is not yet, we don't have numerical values, we haven't actually massed our bolts, and this is what we might call a random interval. It's going to show up somewhere. It's going to be an interval on the real line, but we could shift it left or right. There's different places it may show up. Some are more likely than others. It is a random object. And at this point, there is a 95% chance that the interval that we eventually find, once we make our observations and calculate the confidence interval, there is a 95% chance that the interval we find will contain a population mean. That is part of our interpretation of confidence intervals. Before you've actually made your observations, there is a 95% chance for this particular interval to actually contain population mean once those observations are made. So we're going to get our sample average, we're going to compute an interval. Maybe it really does contain population mean, maybe it does not. There's a 95% chance, based on the math that we've done, that it will contain population mean. Now we actually get our box from company A. We take the 100 bolts, we stick them on our scale, we measure them all, and we find the sample mean to be 7.2 grams. Now we can write down the numerical confidence interval at this point. So we can write down our 95% confidence interval with numerical values, excuse me, with numerical values for the low and the high endpoint of that interval. And it turns out to be 6.808 and 7.592 respectively. So that is an interval of the real line. This is our 95% confidence interval. We think that population mean is in that interval. When I ask you to interpret, or when you just have need to interpret a confidence interval of this type, it is tempting to say there is a 95% chance that mu, population mean, the actual average mass of these bolts, is in that interval. That is not the correct interpretation. You can't say that there's a 95% chance that mu is in this fixed endpoint interval. Mu is an actual number. We don't know what it is, but it's a fixed number. It's not a random quantity. There is an actual average mass for these bolts. And so mu is some number, and this interval has numerical endpoints. There are no random quantities involved at this point in the discussion. So mu is either in that interval or it's not. There is no talk of probability. There are no likelihoods involved. It simply is or is not. Before we had made our observations, when our interval was still random, backing up here one slide, I can say that there is a 95% chance that the interval that I eventually obtain contains population mean. That is legal. But once I have attached numerical values to my endpoints, once I've actually made my observations, and this random quantity has a fixed value at this point, there are no more probabilities involved. I cannot say there's a 95% chance that mu is in this interval, because it either is or is not. Mu is some number. If it turns out to be 6.5, it's not in there. If it turns out to be 7.14, then it's definitely in there. But there's no probabilities involved in that. So again, when our interval was still a random quantity before we had observed sample mean, I can say that there's a 95% chance that the interval that I ultimately obtain once I make my observations will contain mu. And that's true. But once the interval has fixed endpoints, there is nothing random, there are no probabilities, mu is either in there or it's not. I cannot say specifically there's a 95% chance that population mean is between 6.808 and 7.592. That is not correct. Population mean is either between those numbers or it's not. It's not random. There is no probability associated with it showing up in that interval or not. What we are able to say at this point, and this is we're going to think about these questions in a couple of different ways at least, but this is one example of the kind of thing that you could say as if I ask for an interpretation of a confidence interval, and I am likely to do so, this is one type of thing that could be said in such a context. The procedure that we use to produce this interval, the procedure that we use to produce this interval, 6.808 and 7.592, that procedure does successfully produce intervals which contain mu 95% of the time. So I don't know whether or not mu is in this interval, but I know that the procedure that I use to generate this interval successfully or correctly produces intervals which contain mu with a 95% likelihood. And it does so 95% of the time. That's correct. So mu is either in this interval or not. There is no probability associated with that. I don't know whether or not it is, but I know that the procedure I use to generate mu correctly produces intervals. The procedure that I use to generate this interval produces intervals which contain mu 95% of the time. So let's think about this a slightly different way here. What we're dealing with here is a fixed point and a random interval, which may or may not end up containing that point. So mu, population mean, is a fixed point. That's an actual number. We don't know what it is, but it's a number. So that is a single fixed value, and our confidence interval is a random interval, which may end up containing mu or may not. So if we want to think about this in a way that's maybe a little bit more obvious, let's reverse the roles there, and let's think about a fixed interval and a random point. This is more like the type of thing that we're used to thinking about. So I can fix some interval of the real line, and I can ask the likelihood that a random value shows up within that interval. So I can say, for instance, that there is a 95% chance that a standard normal random variable z lands in the interval from negative 1.96 to 1.96. That's true. Before I have observed the actual value of z, when z is still a random variable that has not yet been observed, I can talk about the likelihood that z shows up in that interval. And in fact, it's 0.95. That was part and parcel of what we did in the first part of this lecture when we were developing the idea of a 95% confidence interval. So here I've got a fixed interval with fixed endpoints, and I've got a random number. And I'm saying that there's a 95% chance that that random number, once it's observed, there is a 95% chance that it will turn out to be in the interval from negative 1.96 to 1.96. So that only works when before the actual value of z has been observed. If I go ahead and observe a value for my normal z, and I see it to be negative 0.4, for instance, I'm not going to say that there's a 95% chance that negative 0.4 is in the interval from negative 1.96 to 1.96. That's ridiculous. It is in there. It's a number, and it's in that interval. I don't talk about the probability of a fixed number being in a fixed interval. This is exactly analogous to the fact that when, in the situation that we're dealing with for confidence intervals, there is a fixed number, mu, and there is a random interval, there is a likelihood that that interval ends up containing mu, that it turns out to contain mu, but once a particular value of the interval has been observed, I can no longer talk about the probability of population mean being in that fixed endpoint interval. It's either in there or it's not. In the same way that negative 0.4 is either in this interval or it's not. So you can talk about probabilities when there is still a random quantity involved. When z is still z, we can say there's a 95% chance that it ends up being in this interval. When my confidence interval is still a random interval, I can say that there's a 95% chance that it turns out to contain mu. But once z has been observed, there's no probability as to whether or not that value is in this interval. Just like once my interval has been observed, there's no more talk about probabilities that mu may or may not be in that interval. It simply is or is not. We might not know the answer to that question, so the difference between these two situations is that we don't actually know mu, but it is a fixed number. Alright, hopefully that's helpful. We are going to think about this in a slightly different way now. So we're still working on interpreting confidence intervals. We're going to approach it in a slightly different way. So this time around, we are going to generate lots of confidence intervals, and we're going to think about the 95% idea by thinking about the generation of lots and lots of confidence intervals. So in our example where we were massing bolts, we bought a box of 100 from the company. We wanted to know how much they weighed, so we weighed out those 100, and we found a sample mean of 7.2 grams. And that generated for us a confidence interval, a 95% confidence interval that is shown that we've been discussing. We could buy another 100 bolts. So sample mean, this x sub 100 bar, it is a random variable. Sample mean is random. It depends on the observations that you make. So my first box of 100 bolts, they turned out to have an average mass of 7.2 grams. If I buy another box with 100 entirely different bolts in it, I might see that the sample mean, the average mass for those bolts, turns out to be 6.9 grams. And so for my first sample, I had an average mass of 7.2. For my second sample mean here, I'm seeing 6.9. And I'm putting a little subscript out front here for this being the second sample mean, the sample mean for the second sample. And once I've got that new sample mean, that's going to change my confidence interval. So I find a 95% confidence interval associated with that observation of a sample of size 100, and it takes this form. So we took our first sample of size 100, and that generated the confidence interval. We took our second sample of size 100, and that generated a slightly different confidence interval. And I could continue this process. So I could buy a ton of different boxes of bolts, and for each of them there would be an average mass of the bolts in that box, and that would generate a different confidence interval. Part of this is going back to the idea that was so central to our discussion of the central limit theorem, which is that sample mean is a random variable. Sample mean is a random quantity. And for different observations that I make, I get different sample means, and for different sample means, I generate different confidence intervals. So the confidence interval that I generate, it depends on sample mean, which is itself... How was that? Which is itself a random quantity. Give me 1 second, folks. Something just crashed down in my apartment. I don't know what it was. Huh. Well, that's disconcerting. Alright, we will assume that that was maybe some dishes that were propped up and drying in the other room, and I'll worry about it later. Alright, so... yes, we can make many different observations, and they will generate many different confidence intervals. The idea in the interpretation here is that, so suppose I do this 1,000 different times. I buy 1,000 different boxes, each containing 100 bolts, and each of those samples of size 100 leads to a confidence interval. So I'm purchasing a total of 100,000 bolts here, but I'm doing it in boxes of 100, and I purchased 1,000 such boxes. Each of those boxes gives me an average mass, and each of those average masses, those sample means for a sample of size 100, generates a confidence interval. I end up with 1,000 different confidence intervals, and I've indicated the few of them here, the first, the second, and the last. What it means for these to be 95% confidence intervals is that roughly 95% of these will actually contain the population mean mu. The remaining 5% will not. The whole interval will either be too small or too large, and it'll miss mu. So that is another way of thinking about these 95% confidence intervals. If you generate a ton of them, roughly 95% of them will actually contain the population mean, and the other 5% will fail to do so. So, when you find a particular sample mean and you generate your confidence interval, what you can say, a correct interpretation, is that you do not know whether or not mu is in this confidence interval that you created, but you do know that 95% of all intervals produced using this method will contain population mean mu. So it's another way to think about it. Instead of, there's the two ways that we're talking about today. The first is sort of before you've observed the actual values for your interval endpoints, you know there's a 95% chance of that whatever interval you end up generating actually contains population mean. This new method is, instead of thinking about the probability beforehand, you're sort of thinking about frequency after the fact. So if I generated a ton of confidence intervals using this method, roughly 95% of those would contain population mean, and the other 5% would not contain population mean. These two ideas they're really the same thing. It's the difference between thinking about the probability sort of a priori before you make your observations versus the frequency of the occurrence after the fact. A posteriori, if I want to be a little bit pedantic there. But these are two different ways of interpreting confidence intervals. Once you have an interval of this type with fixed endpoints, you cannot say, and I want to be very clear about stressing this, I do not want people saying that there is a 95% chance that this interval contains mu. Rather, you can say the procedure I used to generate this interval, the 95% of the intervals that it generates contain mu. So it is in that sense that I have a 95% level of confidence that this interval actually contains mu. Hopefully that is helpful. It is a somewhat subtle point, and I am happy to discuss this more either in one-on-one meetings or in office hours. So let me know if you have questions, or via email. All right. So we want to think a little bit more in interpreting confidence intervals. We want to think about what makes confidence intervals get longer, get wider, what makes them get more narrow, what makes them into shorter intervals. Why do we care about that? Do we prefer confidence intervals that are big or confidence intervals that are small? What does all that kind of thing mean? So this is not necessarily like interpreting confidence intervals in a way that would allow you to explain to someone what you have found. That's what we talked about in the first part of this lecture, the first part of part 2 of lecture 20. But this is more about thinking about them yourselves. So us just trying to get a little bit of a better handle on how confidence intervals work, what they mean, and what we can expect from them and what we can interpret from them. So what makes them big or small, and why do we care? Which one do we prefer? So generally, we would prefer to have small confidence intervals. Small confidence intervals are more useful to us. If you could manage to have a smaller confidence interval, that gives you more information in some sense. If I tell you that the population mean for some population is between 0 and 10 to the 10, or some ridiculously huge number, I haven't told you much. There's not a lot of information in there. There's so much room where that population mean could potentially show up that we really haven't narrowed it down at all. We haven't pinned it down in any meaningful way. Instead, you essentially get no information. Like if I tell you that the population mean is between negative infinity and infinity, you get exactly no information. You already knew that. If instead I give you a gargantuan interval of this type and tell you that I think population mean is in there somewhere, that's not super helpful. So if the population, or if the confidence interval for population mean is instead relatively small, so if I tell you I think that the population mean for some population is between, like, say, 2.9 and 3.1, that's more reasonable. Now you have a fairly narrow range of values that you have narrowed down as the only possible values, or the only possible likely values, the only likely values, I should say, for your population mean. So this is we don't have scale to these things. We're not talking about a particular type of population, so there's a lot of open-ended questions. But I'm trying to get across the fact that very large confidence intervals don't convey much. So you don't get a lot of information. There have been cases, so I read and will listen to podcasts from Nate Silver's site, 538. He does a lot of political analysis. He is a statistician. He does a lot of statistical modeling of political races, and also of sports if you're into that kind of thing. I'm not much of a sports guy these days, but I follow politics pretty avidly, and he is a famous and skilled statistical modeler who tries to do a bunch of predictive work when it comes to elections and such. And he'll be the first to tell you that when there's a lot of uncertainty in an election, he may give a confidence interval for how many electoral votes that he thinks, let's say, Donald Trump is going to get in 2020, for instance. So he might come out and say that we think, the confidence interval for the number of electoral votes that Trump is likely to get looks like this. And when it's a gigantic confidence interval, if he were to estimate that Trump's going to get somewhere between 0 and 538, which is the total number of electoral college votes possible, you get exactly no information. If he instead comes out and tells you that he has a 99% degree of confidence that the number of votes that Trump will receive is between 250 and 273, for instance, and I'm just making up numbers here, I'm not even thinking about what the amount that's needed to win, then that's much more information, right? That gives you a fairly narrow range of values, and you actually now have some sense of what's possible from you. So that's the idea. We generally would prefer smaller confidence intervals when we can get them. For the most part, it is hard to get small confidence intervals, and that's the next topic that we're going to discuss. When do you see small confidence intervals? When do you see large confidence intervals? But generally, very wide confidence intervals, they don't pin down the value of mu for you by much. There's still too much freedom allowable in mu for it to be really a useful kind of estimation. So how does the width of a confidence interval change? So here we have our general formula for a 100 times 1 minus alpha percent confidence interval, and it's got several factors. The middle of these intervals are always sample mean, so that's the center of the interval. But then the width is defined by these three factors here. We've got our z sub alpha over 2 factor, we've got the sigma, the standard deviation for the population, and we've got the square root of sample size. It's going to be those three factors that influence the width of a confidence interval. So first, and the one that we generally have the most control over, is n. If we can increase our sample size, that makes the interval get smaller. So the larger our sample sizes are when we're making these confidence intervals, the more narrow, and hence the more useful, are our confidence intervals. And that's really the only tool that you reasonably have to decrease the size of confidence intervals. If you take a small sample, you're not going to have... If you take a small sample, the only way that you can try to reasonably predict a range of values for population mean is if you take a very large range. You just don't have a lot of information, and so you're not really able to pin down where mu is likely to be with any real accuracy without just sort of throwing a very wide net. You have to cast a much wider net to try to catch mu when you don't have as much information. If you can take more samples, so if you can take a larger sample size, then that's going to allow you to narrow your confidence intervals and make those estimations more useful. If sigma increases, the interval is going to get wider, and sigma, remember, is the standard deviation associated with the population itself. So if there is just more variability inherent in your population, it's going to be harder to pin down the population mean. And that's just a fact of life. There's no way around that. The more consistent your population is, then it's easier, the more easily you can gain confidence in estimations for the value of population mean. But if there is inherently a great deal of variability in your population, that's always going to make it harder to achieve small and useful confidence intervals. And finally, there's the level of confidence that you're interested in. So as you desire greater levels of confidence, like going from a 90-degree confidence interval to a 95-degree confidence interval, 90% to 95% to 99% confidence intervals, as that level of desired confidence increases, that means alpha is going down. If you look at our equation here with the 101 minus alpha, that would require alpha to be smaller. That's going to make your interval wider as well. So the more sure you need to be about your estimations, the larger the interval is going to have to be. So I talk about this, or I like to use an analogy here where, like, if I am giving somebody an estimate for when I'm going to arrive at their home, if I'm visiting a friend of mine, they've invited me to their home, and they need me to tell them when I'm going to show up, If the stakes are relatively low, if I don't need to have a great deal of confidence in when I'm actually going to show up, I can give them a pretty narrow window. So if all we're doing is having dinner and I tell them I'm going to be there between 7:30 and 8, say, then if I do happen to be late, if something comes up or traffic is bad and I'm not able to make it there between 7:30 and 8, the worst that happens is I need to give them a quick call and maybe dinner is a little bit cold when I get there. If for some strange reason, like they or their children are going to be murdered if I arrive outside of the window that I provide for them, if I needed to be really sure that I gave them a window in which I could arrive because there were terrible consequences if I did not, then I would want to give them a very wide window. So if I want to be 99+% sure that I'm definitely going to get there in the window that I provide for them, then I would tell them maybe I'm going to get there between 7:30 and next June or something, right? Like I will make sure that I give them a huge window so that I can be very sure that I actually do manage to arrive in that window. So again, if you don't need a large degree of confidence, you're going to see smaller intervals. But if you have to be 99 or 99+% sure, then that's going to require a wider window to achieve that higher level of confidence. So if you desire greater degrees of confidence, or if there is more variability inherent in your population, that's going to make your confidence intervals wider, which is not generally desirable. I mean, it's inevitable, generally, but it's not what you would like to see. And the only tool that you have to make your confidence intervals smaller is to increase the sample size. We should also mention apropos of this, that when we looked at the 90% confidence intervals, we had the 1.64 term. For 95% confidence intervals, it was 1.96. And for 99% confidence intervals, I believe it's 2.58. And you can see there that this z sub alpha over 2 expression gets bigger as the degree of confidence increases, and that's going to serve to make this interval wider. And you could fill in the gaps there. You could think about 94, and you'll see that the z sub 0.06 over 2 is going to be between the values that you would have seen for 90 or 95, for instance. Alright, hopefully that makes some sense. So we generally prefer smaller confidence intervals. It makes good sense why they get bigger when they get bigger and why they get smaller and how that works. And we have also spent some time now thinking about how to interpret confidence intervals once we have found them. In particular, if you have a confidence interval with numerical endpoints, you cannot say there's a 95% chance or a 99% chance or whatever level of confidence that you're thinking about. You cannot say that there is that percent chance that population mean is in that interval. That's not the case. If there's no random quantities, then there is no probability involved. The confidence interval you have found either contains mu or it does not. So instead you have to say something along the lines of the procedure I used to generate this confidence interval has a 95% chance of generating intervals which contain mu. Or the procedure that I used to generate this interval, it generates, out of all the intervals it could ever generate, roughly 95% of them will contain mu. So it is in that sense that I have a 95% level of confidence in this interval, or a 99% level, or what have you. Alright, I thank you folks. We will next time relax the assumption that we know variance. So we'll deal with the case where variance is actually unknown, which is more realistic, and then we'll do lots of examples and sample problems. So we'll get some practice in as well in the next lecture. Thank you folks. Speak to you again soon.